Okay, folks, today what we're going to be doing is we're going to continue where we left off on Tuesday. The goal today is to get through complete net ionic equations using precipitation reactions and acid-base neutralization reactions, and then to start the discussion and hopefully finish the discussion of redox reactions. So a lot to cover today. This is all related to last week's lab. Before I do that, though, I do want to make an announcement about this week's lab. This week's lab is a thermodynamics lab. The lab itself is fast. It usually takes under 30 minutes to perform the entire experiment. But keep in mind that you have to complete the experiment for this week's lab, and you have to turn in last week's lab. Now, you can, if you and your lab partner are in sync, you can turn in this week's lab or last week's lab and turn in this week's lab. That is up to you, because as you saw when you watched the videos, I showed you how to do the mathematics. So you can complete this week's lab if you want, but it's actually not due until the week after Thanksgiving. So the other announcement I want to make is a reminder that next week on Tuesday, we will meet on Zoom. Tomorrow, the Blackboard folder will go live at, like, I think I said it at like 9 a.m. or something. It will go live, and on that front page of that folder, you're going to find the link for the Zoom session next week. So we will not be meeting in person. We will only meet via Zoom. I'll also do my office hours via Zoom next week instead of hosting them in person. Any questions? Yes.
So you're talking about the reaction side from last week. The active homework says it's due Monday. Are you wanting like a paper?
No, you're right. I thank you. You're right. I'm sorry. The active lab, or the lab from last week, is actually not due until Monday because it is due on active. But I recommend trying to finish it today during lab, where you can ask questions if you have questions. That is how I should have stated it. Thank you for reminding me. So once again, today you've got to do the thermodynamics lab. It'll take about 30 minutes. It's up to you how much of the rest of it you do. You have until Monday to turn in your reactions lab from last week. But I would try to finish it up while I'm in lab this week so that you can ask questions. And that way you're ready to turn it in. The thermodynamics lab, it's up to you whether you turn it in this week or whether you turn it in the week after Thanksgiving. You have in the videos that I had you watch with respect to Edpuzzle, I showed you how to do the calculations. So, any other questions? Again, thank you. I'm still trying to wake up this morning too. Okay, so balanced reactions, complete ionic reactions, net ionic reactions. Again, the balanced reaction is probably the least informative of the chemical reactions. It identifies the reactants and it identifies the products, but it really doesn't give any information as to what's going on in the reaction itself. To get to what's going on in the reaction itself, we want to look at the complete ionic. And to go from the balanced equation to the complete ionic, we're going to dissociate all strong electrolytes. And the reason we dissociate all strong electrolytes is because strong electrolytes dissociate entirely in water to form ions. So the complete ionic reaction is going to illustrate how everything appears in solution. Is it in ion form or is it as a solid? What does it look like? Then we can go from the complete ionic to the net ionic equation by removing all spectator ions. Spectator ions are kind of like spectators at a game. They go in hopefully without any, they go in unbruised and hopefully come out unbruised. But they basically go in and come out similar. Whereas the players of the game, they go in and they come out changed in some form, shape, form, or fashion. And so a net ionic reaction is going to show the players, the ones that actually undergo a change during the reaction process. Now, we're going to use the balanced chemical equation, complete ionic reaction, and net ionic reaction with two types of reactions that we're going to discuss. The first type that we're going to use it with is going to be called a precipitation reaction. A precipitation reaction is simply going to be a reaction that forms a solid product. For our purposes, we are going to be focused on ionic compound or reactions of ionic compounds. So in other words, you're going to follow your solubility rules to figure out if something is a precipitate or not. To a large extent. The only exception to that is if we're actually making a metal. The second type of reaction we're going to work with is going to be an acid-base neutralization reaction. In an acid-base neutralization reaction, you're going to react an acid that will be aqueous with a base that will be aqueous. And all right, let me rephrase that base. You will react it with a base. But you're going to have to look at your solubility rules. For ionic compounds. And that is going to go to form water in liquid form. Stop. And a salt, which again, you'll look at your solubility rules. To discern. So those are the two types of reactions that we're going to look at performing acid-base neutralization reactions with. I mean, two types of reactions we're going to look at to perform complete net ionic reactions with. So going back up to some of the things that we did last week, we did potassium, the lead 2 nitrate. Reacting with potassium iodide to form lead 2 iodide and potassium nitrate. As a reminder, we focused on the solubility rules because these are all ionic compounds. Rule number 1 says that if it includes a group 1 metal or if it includes ammonium, it is going to be soluble and there are no exceptions. So therefore, our potassium iodide, because it contains a group 1 metal, is going to be a soluble ionic compound, and therefore it is going to be aqueous. Our potassium nitrate is going to, because it contains a group 1 metal, is going to be a soluble ionic compound. Therefore, it is going to be aqueous. Rule number 2 says if it contains nitrate, acetate, perchlorate, or bicarbonate, it is going to be soluble with no exceptions. Because lead nitrate contains nitrate, it is going to be a soluble ionic compound, meaning it is going to be aqueous. By the way, once you assign a state of matter, you don't need to look at that compound again. So although potassium nitrate also includes nitrate, I didn't need to look at it again because I'd already assigned it a state of matter using the potassium. Now, rule number 1 and rule number 2 knocked out 3 of our 4 compounds. The 4th compound, we're going to have to follow the anion to determine how it behaves. And according to the 3rd rule, halides are soluble except if they're attached to silver plus, lead 2 plus, or mercury 2 plus. Since this halide is attached to lead 2 plus, that makes this an exception. And so this is an insoluble ionic. And so it is a solid. Folks, all I've done is repeat what I said on Tuesday so far. But now we're going to add what we just learned. This is a precipitation reaction. Because lead 2 iodide is a solid. And that's what it means to be a precipitate, is you form a solid. We're also now going to apply the complete net ionic. So to apply the complete net ionic, we've got to decide, is it a strong electrolyte or not? Because again, we're going to dissociate strong electrolytes. Those are the only ones that get dissociated, are the strong electrolytes. Lead nitrate, because it is a soluble ionic, is a strong electrolyte. Potassium iodide, because it is a strong soluble ionic, is going to be a strong electrolyte. Potassium nitrate, because it's soluble ionic, is going to be a strong electrolyte. But the lead iodide, because it is an insoluble ionic compound, is going to be a weak electrolyte. So when we go from the balanced chemical equation, which I just balanced as I was going through this, to the complete ionic reaction, we need to break apart everything but the lead iodide into its ions. Hence the name. Complete ionic. We're going to break it apart into its ions. So what is the cation in the lead 2 nitrate? Lead 2 plus. And what is the anion in lead 2 nitrate? Nitrate. And what is the formula for nitrate? NO3 minus. The ions will have the same state of matter as their parent compound. So since the parent compound was aqueous, the ions will also be aqueous. Now we have to do something else too. This needs to be balanced. Well, from the lead nitrate, it was 1 lead and how many nitrates? 2. So we need a 2 out in front of the nitrates. Now our potassium iodide, what is the cation? Potassium, and what's its formula? K plus. And what's the anion? I what? What's its charge? I minus. The ions will have the same state of matter as their parent compound. So since the parent was aqueous, the ions are aqueous. But this is a balanced equation. So we got to do something with that coefficient of 2. That coefficient of 2 means that there were 2 potassiums and there were 2 iodides. Now, the lead 2 iodide was an insoluble ionic compound, so it's a weak electrolyte. We didn't say anything about the weak electrolytes, so you're going to just bring those weak electrolytes down just the way they look. You're not going to alter them at all. So that's PbI2 solid. You only bust up the strong electrolytes. And then we have potassium nitrate. What is the cation? Potassium. And what is the anion? Nitrate. And its formula is NO3 minus. The ions will have the same state of matter as their parent compound. And we do have to do something. This has to be balanced. So since there are 2 potassium nitrates, that means that there are 2 potassiums and 2 nitrates. That, folks, is the complete ionic reaction. It is illustrating what everything looks like in solution. Now, once you get to the complete ionic, getting to the net ionic's a breeze. It's the complete ionic that's the challenge. Because the net ionic, to get to it, you're going to remove your spectators. Spectators appear the exact same way on the reactant side as the product side. So let's just talk through it. I have lead 2 plus on the reactant side, aqueous. Do I have lead 2 plus aqueous on the product side? No. I have 2 NO3 minus aqueous on the reactant side? Do I have 2 NO3 minus aqueous on the product side? Yes. So nitrate is a spectator. I have 2 K plus aqueous on the reactant side. Do I have 2 K plus aqueous on the product side? Yes. So K plus is a spectator. I have 2 I minus aqueous on the reactant side. Do I have 2 I minus aqueous on the product side? No. Once you get through going back and forth through the reactants, whatever's left comes down into the net ionic reaction. This is the substances that undergo a change during the reaction process. So that bright yellow solid you saw last week that appeared out of 2 clear colorless solutions was lead 2 iodide. Questions? So what are the most common mistakes I see? Well, one common mistake I see is people forget charges. It's called a complete ionic reaction. In other words, I better see charges. Second mistake I tend to see is people want to not only bust up the ions, but they want to bust up the polyatomic ions. If it's a polyatomic ion, it does not get busted up. Polyatomic ions come down as a polyatomic ion. Those are common errors that I see. The other common error is just, the other common error, and this one's a big one, is something we actually discussed on Tuesday. And that is, you cannot simply pick up and move an ion. You gotta go back to its actual form. You gotta go back to its actual form. So that's probably the most common mistake I see is people want to just pick up and move so that they would move this nitrate 2. They want to move nitrate 2. You can't move nitrate 2 because the ion is not nitrate 2. It's just plain old nitrate. Those are the most common mistakes I see. Whoops. Let's look at another one. Yes.
With the precipitation reaction, it's also a double displacement, but does the precipitation always outweigh the double displacement whenever you're naming what they're doing?
No. You can put both of them. If it's a double displacement and it's precipitation, you can write both. It all depends upon what you're trying to discuss, whether you're trying to discuss just what it appears like or whether you're actually describing what goes on, is basically what it boils down to. Yes.
So the longer reaction is the complete reaction, and then the one without the spectators is just the net.
Correct. Other questions? Okay, so let's look at this one. We determined it was magnesium solid plus 2HCl aqueous goes to form magnesium chloride aqueous plus hydrogen gas. This was one of the single displacement reactions we were working with. We can write complete and net ionic equations for this as well. It's not a precipitation reaction, but we can get to the complete and net ionic. We're going to do the same thing. We're going to ask ourselves, what type of compound is it? Is it a strong electrolyte or a weak electrolyte or a non-electrolyte? You don't have to even think about it if it's a solid, liquid, or a gas. If it's a solid, pure liquid, or a gas, those are gonna just stay as they are. Pure solids, pure liquids, pure gases are not electrolytes. Pure solids, pure liquids, and pure gases are not electrolytes. It's only aqueuses that we got to look at. Only aqueuses can be an electrolyte. So, looking at this is a non-electrolyte. HCl is a strong acid. And strong acids are strong electrolytes. Magnesium chloride. It's a soluble ionic. Soluble ionics are strong electrolytes. But hydrogen is a non-electrolyte because it is a gas. So, to go to our complete ionic, magnesium is just going to come down as it appeared. Because to go from the balanced chemical equation to complete ionic, you only break apart your strong electrolytes. Now, hydrochloric acid, we said, is a strong acid and therefore a strong electrolyte. We got to break it into its ions. What's the cation? H plus. And what's the anion? Cl minus. The ions have the same state of matter as their parent, and we do have to take into account the balanced chemical equation. There's 2 hydrochloric acids. That means there's 2 hydrogens and 2 chlorides. Magnesium chloride, we said, was a strong electrolyte because it's a soluble ionic compound. So we're going to break it apart into its ions. Its ions are magnesium ion and chloride ion. The ions will have the same state of matter as their parent. But the ion is simply Cl minus. The fact that there are 2 is there to balance the cation. So that becomes a coefficient in the net ionic. And then you have hydrogen gas, which is a non-electrolyte. And that, folks, is the complete ionic. To go from the complete ionic to the net ionic, you remove spectators. They're the things that appear the exact same on both sides of the equation. The only thing that appears the exact same on both sides of the equation is the chloride ion. Everything else changed. So the complete or the net ionic equation is magnesium solid plus 2 hydrogen ion gas, aqueous, goes to magnesium ion aqueous and hydrogen gas. Yes.
So we don't ever count solid liquids or gases when we're considering what's the same in the reaction.
Solids, liquids, and gases are always non-electrolytes.
So they're never gonna be in there.
They're never going to get busted up. Questions? Let's look at one more. Last Tuesday, we had hydrochloric acid reacting with sodium hydroxide to form water and sodium chloride. Hydrochloric acid is one of your strong acids. So this is a strong electrolyte. Dr. Taylor just blew up a hydrogen balloon. That's what that boom was. Sodium hydroxide was soluble ionic. So it is a strong electrolyte. Water is a pure liquid. So it's a non-electrolyte. Sodium chloride is a soluble ionic. So it's a strong electrolyte. This, folks, is also an acid base neutralization reaction. It's an acid. The acid's obvious. The base, not so obvious. But it's sodium hydroxide. And if you'll recall, I said strong bases are oxides and hydroxides of group 1 metals. And it went to make water and a salt, where the salt was an ionic compound. So this is an example of an acid-base neutralization reaction. Now, to get to the complete ionic, we got to break up everything but the water. Hydrochloric acid, the cation is hydrogen, the anion is chloride. The ions have the same state of matter as the parent. Sodium hydroxide was a strong electrolyte because it was soluble ionic, so we're going to break it into its ions. Its ions are sodium plus and hydroxide minus. The ions will have the same state of matter as the parent. That goes to make water. We're just bringing water down because the only thing we ever break up are the strong electrolytes. And then we have sodium chloride. Sodium chloride is a soluble ionic compound, so we're going to break it up into its ions of sodium ion and chloride ion, where the ions have the same state of matter as the parent. And that is the complete ionic reaction for the strong acid, strong base neutralization reaction between hydrochloric acid and sodium hydroxide. To get to the net ionic equation, we're removing spectators. Those spectators are going to be chloride and sodium. So our net ionic equation is going to be H plus OH minus goes to form water. A note. This will always be the net ionic equation for a strong acid strong base reaction unless there is an exception to this, unless the acid is sulfuric acid. Then you'll have to actually figure it out. That is because of the fact that if it's reacted with calcium, if you react sulfuric acid with calcium, strontium, or barium, you make a solid. So that changes everything. And I do want to highlight strong acid, because if we alter the acid to be a weak acid, it also will change it too. So, which I will do a weak acid, but I want to make sure that you have everything you need to do the lab. So I may have to pick up with a weak acid on Tuesday at the start of lecture. But I want to make sure you have everything you need to complete last week's lab first. Any questions about some of the stuff I've done? It takes practice. It seems straightforward for the most part when I'm saying it, but it's not as easy when you actually have to do it. It does take practice. Okay, so what we're gonna do now is we're gonna move into redox reactions. The term redox is actually a combination of reduction and oxidation reactions. Oxidation and reduction have to occur simultaneously. You can't have one without the other. Now, to help remember oxidation and reduction, you can use the term oil rig. Oxidation is loss of electrons to form a more positive charge, a more positive oxidation state. Reduction is gain of electrons to form a less positive or even negative oxidation state. Now, the reducing reactant sometimes referred to as the agent, causes another element to be reduced. While an element within it becomes oxidized. What I like to point out is we still have redox. The oxidizing reactant causes an element to be oxidized. While an element within the compound becomes reduced. Again, you still have redox. So basically, folks, this hinges on you being able to identify the oxidation state so that you know what element is being oxidized and what element is being reduced so that you can figure out who the oxidizing reactant is and who the reducing reactant is. So it all hinges on oxidation states. Rule number 1. An element in its standard state has an oxidation number equal to 0. You'll recognize it because it will be a compound. Let me rephrase, it'll be a neutral compound. Of an element. That's all it's going to be, is an element. Rule number 2. Ions have the same oxidation number or have an oxidation number equal to its charge. So cations in an ionic compound, their oxidation number will be the same as their charge. Anions, elemental anions in an ionic compound, their oxidation state will be the same as their charge. Those two have no exceptions to those rules. Then we get into exceptions. Rule 3, hydrogen will have a +1 oxidation state unless the only other element is a metal. Then hydrogen's oxidation state will be a -1. 4, oxygen will have a -2 oxidation state unless in a peroxide. Then it has a -1 oxidation state. Five, halogens have a -1 oxidation state except if combined with oxygen and then you must calculate or if combined with another halogen and then the smaller atomic size gets a -1. and the larger one must be calculated. And folks, I believe I put these, a sheet of these on Blackboard. All other elements must be calculated. The same way you calculated the charge on a metal whose charge varied. Okay, we're gonna apply this. So let's apply this to that single displacement reaction we've been working on with the magnesium solid reacting with 2 hydrochloric acids to form magnesium chloride aqueous plus hydrogen gas. Today, we developed the complete ionic magnesium solid plus 2H plus aqueous plus 2Cl minus aqueous going to form Mg2 plus aqueous plus 2Cl minus aqueous plus H2 gas. And we then went on to develop the net ionic equation as magnesium solid plus 2H plus aqueous going to form magnesium ion plus H2 gas. We're going to apply our oxidation rules. To our net ionic equation. And we're gonna answer the element oxidized. The element reduced. The oxidizing reactant. And the reducing reactant. Okay, rule number 1 says an element in its standard state has an oxidation number of 0. That means the magnesium has an oxidation number of 0 because I said that to help you recognize it, it's going to be a compound that consists of only one type of element and it's going to be neutral. Hydrogen is also going to have an oxidation number of 0 because it is a compound that consists of only one type of element and it is neutral. The next rule said that elements in there that are, excuse me, it says ions will have the same oxidation number as their charge. So hydrogen, since it's a +1 charge, it's going to have a +1 oxidation state. Magnesium, because it's a 2+ charge, is going to have a +2 oxidation state. And you may have always wondered why I put when I was writing ions, I always put magnesium 2+ or chromium 3+ instead of +3. I did that to distinguish between what's a charge and what's an oxidation state. So charges, I always write the number before the sign. Oxidation state, I always write the sign before the number. Now what we're going to do is to get these first two, we're going to apply a number line to this. If it moves in a more positive direction, because oxidation is loss of electrons to become more positive, then it's going to be oxidized. Reduction is loss of electrons. Reduction is gain of electrons to become more negative or less positive. So that means it would be reduced. So using a number line, we can identify who's oxidized and who's reduced. Now what we're going to do is we're going to connect our elements. Magnesium goes from a 0 to a +2. So because it's moving in a more positive direction, magnesium is being oxidized. Hydrogen is going from a +1 down to a 0. So hydrogen is being reduced. Now to answer the last portion of this. And this is where those rules apply. I think this class overheats my tablet. Going way back up here, the reducing reactant is going to contain the element oxidized. So the element oxidized, again, remember our redox. Element oxidized has to be with the reducing reactant. So what we're going to do is we're going to look back at the reactant that contained the magnesium. And when we look back at the reactant that contained the magnesium, it was magnesium solid. So that is our reducing reactant. The element reduced is in the oxidizing reactant, again, redox. So we find the element reduced, which was hydrogen. Hydrogen was originally in hydrochloric acid, so the oxidizing reactant is HCl. And that's how you sort through oxidation and reduction. Yes.
For the HCl, we do not need to put that it's aqueous.
No. You just, because it's just asking what the reactant is that's responsible.
So what's the difference between that and MGS?
I could have put it, it does not matter, to be honest. It didn't matter really. Yes.
That's oxidation state.
What now?
You show the oxidation.
These?
Yes.
Okay. I will do a calculation real quick of an oxidation state. Because you will have to do it on the homework. So on the homework, I think I've got you writing 3 complete ionics, 3 net ionics, and 4 or 5 oxidation states is what's on the homework that's due on Monday night along with your lab. So I do want to do one. Did you have enough time? Okay. So let's just look at a calculation real quick. Let's say I have P4O5. We can assign oxygen a -2 oxidation state because according to the 4th rule down, oxygen is a -2 unless it is a peroxide. And I will tell you if it's a peroxide. So it's going to be a -2 most of the time, in other words. And then you go to rule number 6 before you even get to phosphorus and you find there's no rule about phosphorus. That means you're going to have to calculate phosphorus's oxidation state. So there is 4x minus 10, and that is equal to 0. 4x equals 10. X therefore equals 2.5. Come on, catch up. And yes, you can have fractions for oxidation states. 5 times the -2. If you have sulfate, for example, oxygen is a -2 because of rule number 4. Sulfate, or the sulfur, you have to calculate. We have X -8, and that is equal to a -2 because the sulfate ion is charged. X equals a +6. Did not put a 0. Yes. That's the oxidation number for, or oxidation state for sulfur. The neat thing about polyatomics, folks, once you find the oxidation state for a polyatomic, the oxidation state remains the same. So if, no matter where I go find sulfate, whether it is in lead 2 sulfate or sodium sulfate or whatever, if I have sulfate, the oxidation state of the sulfur is a +6, and the oxidation state of the oxygen's a -2. It doesn't matter where you find it. With that, I will see you in lab for a quick experiment, and then you can work on the rest of the lab from last week, or, I mean, it's up to you what you do, but I will be there to answer questions. I'm gonna see if this thing can cool off.